This is the 12th session in our decision tree series. In this video, we'll explore decision trees for multi-class classification. In the previous 3 videos, we examined cost-complexity pruning in detail. This session is the final part of CART decision trees for classification, where we extend those ideas to the multi-class case. We'll look at how entropy and the Gini index are calculated when there are multiple classes, and how the misclassification rate is calculated in cost-complexity pruning. We will not cover all aspects of multi-class classification, but instead briefly focus on the differences from binary classification. Finally, we'll implement a multi-class classification model using scikit-learn's DecisionTreeClassifier. Up to this point, we have focused on binary classification with 2 target classes. However, even when there are multiple classes, entropy and the Gini index can still be calculated using a generalized formula. In this formula, C represents the number of classes. For example, if there are 3 classes, then I takes the values 1, 2, and 3. With this formula, entropy is calculated in the same way as in binary classification. And the same applies to the Gini index. Let's look at an example. Suppose node T contains 7 data points from class 1, 3 data points from class 2, and 2 data points from class 3, for a total of 12 data points. First, we calculate the entropy contribution for class 1. Since 7 out of 12 data points belong to class 1, this gives us the following result. We then repeat the same process for class 2 and class 3. By summing these values, we obtain the total entropy of the node, which is 1.384. Using the same data, the Gini index can be calculated, resulting in a value of 0.569. In binary classification, the maximum values of entropy and the Gini index are 1.0 and 0.5 respectively. However, in this example, both values exceed those limits. Let's understand why this happens and determine the maximum values in the multi-class case. In general, the maximum entropy is the log base 2 of the number of classes, and the maximum Gini index is 1 minus 1 divided by the number of classes. Both entropy and the Gini index reach their maximum when all classes are equally likely. That is, when each class has a probability equal to 1 divided by the number of classes. In binary classification, since the number of classes is 2, the maximum entropy is 1.0. And the maximum Gini index is 0.5. When the number of classes is greater than 2, the maximum entropy becomes greater than 1. And the maximum Gini index becomes greater than 0.5. Let's verify this with a simple example. Assume a node contains 9 data points, evenly distributed across 3 classes, with 3 data points in each class. Since the classes are perfectly balanced, the impurity is maximized. Therefore, both entropy and the Gini index reach their maximum values. In general, if a node contains n data points in C classes, the impurity is maximized when each class has n divided by C data points. This corresponds to each class having a probability of 1 divided by the number of classes. If we substitute this probability into the entropy formula, we obtain the maximum entropy, which is log base 2 of the number of classes. Similarly, if we substitute this value into the Gini index formula, we obtain the maximum Gini index, which is 1 minus 1 divided by the number of classes. Using these measures, we can compute information gain just as we did in binary classification, allowing us to determine the optimal split and construct the decision tree. Next, let's examine how to identify the weakest link in cost-complexity pruning for multi-class classification. We covered the pruning process for binary classification in detail in the previous videos, so here we will focus only on what is different. Let's consider the following tree, which includes 3 classes, blue, red, and green. As before, we compute the alpha star value for each internal node and identify the weakest link. For more details on these formulas, you can refer to the previous videos. Let's compute the cost complexity measure for node T3. In binary classification, the misclassification rate is defined as the proportion of samples belonging to the minority class within a node. Whereas in multi-class classification, it is instead defined as 1 minus the proportion of samples in the majority class. At node T3, there are 18 data points, 8 of which belong to the majority class. Therefore, the misclassification rate is 1 minus 8 divided by 18. Since this node accounts for 18 out of the total 24 data points, we multiply by a weight of 18/24. Finally, by adding the penalty term alpha, we obtain the cost complexity value for node T3. Repeating this process for all internal nodes gives us their respective alpha star values. Among them, node T5 has the smallest alpha star, making it the weakest link. The remaining pruning process is identical to the binary classification case. Next, let's implement a multi-class classification model using scikit-learn's DecisionTreeClassifier. We will use the extended iris dataset, which consists of 1,200 data points, each with 20 features and 1 target variable. This dataset is available for download at the following link. We load the dataset and encode the categorical variables into numerical values. We then separate the features and the target variable and split the data into training and test sets. The target variable consists of 3 classes, 0, 1, and 2. To simplify the model, we will use only 5 of the 20 features. Next, we build a fully grown decision tree using DecisionTreeClassifier, identify the weakest links, and then apply cost complexity pruning to find the optimal tree. This implementation is the same as in the previous video, so please refer back if needed. We then visualize how the accuracy changes on both the training and test sets as alpha varies. As shown in the results, we select the model that achieves the highest accuracy on the test data as the optimal model. Using the optimal model, we predict the classes of the test data. The model's predict_proba function gives the probability that each data sample belongs to each class. We can classify each sample as the class with the highest probability. For example, for the first test sample, the probability of class 0 is 0%. The probability of class 1 is 95.2%. And the probability of class 2 is 4.8%. The first data sample is classified as class 1, since class 1 has the highest probability. The training accuracy is 95.11%, and the test accuracy is 94.67%. Now let's run this code. The results are consistent with what we observed earlier. So far, across 8 videos, we have explored cart decision trees for classification in detail. In the next video, we will move on to cart decision trees for regression. See you in the next video.